One of the most common questions asked when learning about asynchronous programming is why asynchronous programming? What are the advantages? It turns out we can look at a simple example to understand the advantages. Every day, there's some new developer out there. They're getting stuck with loading a CSV file so they can total up some column. They've been given this job. It's almost a rite of passage. Everyone's going to have to do it someday. And the first is kind of a first early step into data analytics. So a new developer might load the entire CSV file into memory, calculate what they need to know, and then print out the answer. They excitedly declare success, only to have their program crash when processing a 20 gigabyte large CSV file. Okay, maybe the last part just happened to me. Either way, it's a bad thing. So, at this point, a more experienced developer is probably already thinking about streaming interfaces and iterators and how they're going to process this file piece by piece. They might be surprised to know that there is another way that they could handle this problem, and they probably even know what this way is. It's just been rejected for so long that they've been indoctrinated not to even consider it. I'm talking about paging. Yes, you're probably already laughing at the idea. Let the OS swap the currently unused parts of the CSV file to disk. Allow the program to over-allocate the limited resource, memory, and rely on the OS to schedule it. Now, I know what you're thinking. You're probably thinking of all kinds of reasons that paging is a terrible idea. Hold on to those reasons. I'm going to bring them up again in a minute. Now let's pretend our task is getting a little bit more complicated. We're going to read multiple large CSV files. Ah, you say. We can use threads to read all those files at the same time. That's true. We can also use threads to parse batches of rows at the same time and speed up our parsing. That's also true. This is getting exciting. But wait, we're dealing with another limited resource here, CPU cores. We may have 20 files, and each file may have 10 columns, but we probably only have 4, 8, some small number of CPU cores. Never enough. That's okay. You can always create more threads than you have cores. But hold on there. You remember all those anti-paging ideas you had earlier, and why it was a terrible idea? Why don't those apply here? We're over-allocating a limited resource. We're over-allocating our cores by creating more threads. Then we rely on the OS to schedule access to the resource for us. That's right, we run into the exact same problem. Instead of paging, we have context switches. And it's the exact same thing. We have to spend time swapping out these different threads onto the cores. Now, you might reply, well, it's expensive to swap pages out to disk, and it's pretty cheap for a context switch. And that's true, but in the right situation, context switches can add up, and even though they don't cost much, if you have enough of them, they'll start to drag down your performance. Then you might say, well, I can always create a thread pool. I can take all these tasks I have, and I can put them in nice queues here so that they'll get processed in order, and I'm not creating more threads than I have cores on the system. Well, we're getting closer, but now you have some more problems. What happens if one of your tasks is waiting on another task and it gets scheduled first? It blocks that entire core. If that happens on all of your cores, suddenly you have a deadlock. Okay, you say, well, I can be smarter about how I put things into these queues. Maybe I can express these task dependencies in some way. And so you come up with a more clever algorithm so that the blocking tasks are always at the end. But then you still have another problem, which is you've got some of these tasks are going to be blocking. They're going to be running I/O or doing something that's slow. And now what happens if you have a new kind of cheap task that comes in, and it could be running right now, but you're spending time on that thread pool just sitting around waiting for I/O? Well, now you have to get even more complicated about how you're going to schedule all of these things onto this queue. And it starts to become a far more complicated problem. And at this point, there is a natural solution, which is to just give up. And that's probably the most common approach to this problem. You just say, well, you know what? A context switch is a necessary evil. It's not that expensive. I'll optimize away the few places where I have a ton of context switches, and life goes on. And that works. That works for quite a number of processes. But it still feels like we're giving up and that there could maybe be a better way. So let's try and take this a little bit further. So now, as a more complicated approach, we could create a fast lane, and we could create a slow lane. The slow lane could be all of our blocking tasks, and there's only ever one task from each lane that's actually scheduled with the OS. Now, the slow task is going to spend most of its time in the waiting state, and so the OS is going to keep the fast tasks on the core for most of the time, and this works pretty smoothly. And you might think at this point that, I've solved this problem. You don't need async. You don't need any of these fancy non-blocking techniques. But the truth is that you've just recreated async. This is exactly how async works. Async processing is about keeping a fast lane for your non-blocking tasks and slow lanes, or no lane at all, for your slow tasks. Later, I'll cover how that works, but as a spoiler, in order to be able to create this fast lane and slow lane, we need all of those non-blocking APIs, callbacks, promises, async await. Those are all tools to help us create a fast lane and a slow lane. So, async processing is about creating a fast lane so that we can reduce the number of threads that we need, so that we can reduce the number of context switches that we encounter. And that's why async programming can often give you better performance on a number of tasks. One example that's been popular recently is web server development. Web servers may have to serve thousands of concurrent requests per second. And web servers are often just doing a tiny amount of CPU work before they farm the request off to a database or to other servers in the backend that are actually doing the processing. So you have a large amount of I/O, a large amount of threads, and a very small amount of CPU work. And that's the perfect situation for async, because we can prevent all of the context switches we would have otherwise from all of these thousands of threads constantly sending out I/O requests and getting back responses. And we can optimize that tiny amount of CPU work to run on a much smaller set of cores than we would otherwise need. So I hope this helps explain the advantages of async and why async. And then later, we can explain why async is so hard to actually implement.